All right, so today we're diving into some seriously mind-bending stuff. Quantum mechanics.
Yeah.
But like not the usual intro stuff. We're going deep.
Yeah, we're going way past the basics. Quantum mechanics, it's kind of a big deal. It's the backbone of pretty much all modern science. And it's got this amazing track record for nailing how the universe works at the tiniest levels.
Exactly. Like it's not just some abstract theory. This stuff is real. It's powering the tech in our pockets.
Yeah.
And it's shaping our understanding of, what the universe is actually made of.
Absolutely. From the chips in your phone to the behavior of those fundamental particles, it's all quantum mechanics, and we're going to explore a really fascinating aspect of it today.
So the way we often learn quantum mechanics, this weird thing, right? It's called wave function collapse.
Right. The idea is that a quantum system, let's say an electron, can be in multiple states at once, a superposition. But when we try to measure it, boom, it picks one state. Like our act of looking forces reality to choose.
Yeah, it's so bizarre. Like our observation makes reality snap into focus or something. And that's the traditional view, the Copenhagen interpretation.
Exactly. And that interpretation, it gives us two distinct ways quantum states can change. First, there's that sudden, unpredictable jump into a definite state when we observe it. That's process one.
Right. Process one, the jump.
And then we have process two, which is the smooth, deterministic evolution of an isolated system. That's all driven by the equations of quantum mechanics.
Okay, so process one is the jump when we look, and process two is the smooth evolution when we don't.
Got it.
But what if there's a way to look at quantum mechanics that completely ditches that jump?
Well, that's what we're going to dig into today.
Okay, I'm intrigued. Tell me more.
It all starts with Hugh Everett III and his relative state formulation of quantum mechanics.
Okay, relative state. Sounds intense.
Oh, it is. You see, his work came from some really deep questions that popped up when physicists tried to mesh quantum mechanics with, gravity.
Yeah, gravity. Always got to be gravity.
Always. So think about it. When you're talking about the entire universe, how do you even define an outside observer? If we want a theory that explains everything, the idea of an external observer triggering changes feels, well, incomplete.
Yeah, that makes total sense. If the universe is everything, then who's outside to look at it and make it collapse?
Exactly. And Everett saw that. He wanted a theory that was more fundamental, more comprehensive, one that could maybe even explain the standard interpretation we know.
Okay, so he wanted to unify things, find a deeper level.
Right. And the truly radical part is, his formulation just tosses out those special rules about observation. No more observer needed for things to happen.
Wow, hold on. No built-in observer causing collapses. That sounds like a completely different way of thinking about quantum mechanics.
It totally is. And that's what makes this deep dive so interesting. We're going to see how Everett's relative state formulation tackles that whole wave function collapse mystery. What if, instead of collapsing, all the possible outcomes of a quantum measurement actually happen, each playing out in a different, constantly branching universe?
Wait, hold up. Branching universes, are we talking about the multiverse?
That's the term that's stuck, yes. Now, Everett didn't explicitly use multiverse in his original work, but the idea is there. The universe effectively splits with every quantum measurement. Each new universe represents a different outcome. And boom, no more need for process one, that discontinuous jump.
Okay, so it's not like our electron in a superposition picks one state when we measure it. Instead, it goes into every possible state, and the universe splits to accommodate all of them. So there's a universe where we see spin up, another where we see spin down, and so on.
You got it. It's a fundamental shift. Not one reality winning out, but all possibilities becoming real. And then we have to figure out why we only experience one outcome. Why don't we see all these branches?
Right, because I definitely don't feel myself splitting every time I look at something. So to really get this, let's take a step back. What were the big issues with the standard external observation idea that led Everett to this new approach?
Great question. One major problem that Everett pointed out was this fundamental asymmetry in the standard interpretation. It treats isolated systems differently depending on whether there's an observer inside.
Okay, so if a system is alone, it follows the rules of process two, the smooth evolution. But if someone's watching, boom, process one takes over.
Exactly. Imagine you're doing a quantum experiment in a sealed lab, completely isolated. You take a measurement, and supposedly, process one happens.
So if that lab, me included, was perfectly cut off from the rest of the universe, would the laws of physics suddenly change?
That's the problem. Does an observer really have that kind of power to change things just by looking? It seems odd. Everett argued it shouldn't be that way, he asked. can't an isolated system with an observer still be described by the continuous evolution of process 2? Where does this special process 1 come from?
It's like giving the observer some magical ability to alter reality.
Right, and it gets even weirder when we think about the whole universe. Who's observing the universe?
Yeah, if it's everything, there's nothing outside.
So how can its wave function collapse? That idea of an external observer, even the concept of energy conservation, it gets really tricky to apply to the entire cosmos.
Mind-blowing stuff. So the idea of an external observer causing a collapse just doesn't make sense for the universe as a whole.
Exactly. And another issue was approximate measurements. The standard formulation, with its projection operators, struggled to handle situations where measurements weren't perfect. Like what happens if the measurement takes some time or there's some noise?
So real-world messiness.
Yes. In those cases, it was tough to predict what the system would do and what the probabilities would be. So the core problem was this reliance on external observation, process 1, which seemed arbitrary and didn't quite fit with how we think fundamental physics should work, especially for isolated systems or the whole universe.
Got it. The standard picture had these big conceptual holes. So how did Everett try to fix them? What's this relative state foundation he came up with?
Okay, so Everett's relative state formulation, it starts with a completely different principle, he said. Forget about process 1. Pure wave mechanics, process 2, that smooth, deterministic evolution described by the Schrödinger equation, that's all you need to describe any isolated system. No exceptions.
So no special rules when an observation happens. Everything just follows the flow of the wave function.
Exactly. External observation, it's not fundamental. The systems we observe, they're just parts of bigger isolated systems. And the wave function itself, that's the main thing. We understand it by looking at the theory's internal logic, not by adding rules about observation from the outside.
Okay, that's a pretty big shift. But if everything's just the wave function evolving smoothly, how do we get those definite outcomes that we see in experiments?
That's where the amazing idea of relativity of states comes in.
Okay, relativity of states. Lay it on me.
Imagine a composite system, like an observer and the system they're measuring. When they interact, they get entangled. Their quantum states become linked.
Entanglement, like
Yeah.
when two particles are linked, and measuring one tells you about the other instantly, no matter how far apart they are.
Perfect analogy. And this entanglement, it means the individual parts don't have independent states anymore. The state of one part only makes sense relative to the state of the other part.
It's like they're dancing together. You can't describe one dancer without the other.
Exactly. Mathematically, the overall quantum state of this composite system is usually a mix of different possible states for both parts. But you can't just say part 1 is in this specific state and part 2 is in that specific state. They're intertwined.
So we need this relative state idea to make sense of it. If I pick a state for the first part, then there's a specific relative state for the second part that's entangled with it.
You got it. For any state of one part, you can figure out the corresponding relative state of the other. And that relative state tells you everything about the probabilities of different measurements you could get for that second part, given the first part's state.
So it's not about the measurement forcing the system to a single state.
Yeah.
It's more like the interaction creates this relative state between the observer and the observed system. All the possibilities are still there in the combined wave function.
Exactly. To see this in action, let's look at the von Neumann model of measurement. Imagine our electron with its spin, and we have a measuring device to detect that spin. Initially, they're separate, each with their own wave function.
Independent, like two ships passing in the night.
Perfect. But when they interact, the total wave function for the electron and the device, it evolves according to the Schrödinger equation. They become entangled.
So they're not separate anymore. The device isn't just passively reading the electron's spin. It's part of this new entangled state.
Right. But here's the key. We can look at this total wave function in different ways. We can think of it as a sum, a superposition, where the electron has a definite spin, up or down, and the device shows that value.
So it's like saying electron spin up and the device reads up, plus electron spin down, AD the device reads down. Both possibilities are still in the math.
Absolutely. You could also look at it from the device's perspective. The device shows a value, and the electron is in a relative state that matches that value. The point is, the electron doesn't actually jump into a single state. That's just how it looks from a particular perspective.
It's like saying the collapse is just a way of looking at things, not a real physical event.
Precisely. The measurement just creates these correlations. The device's state only makes sense relative to the electron state, and vice versa. All the possibilities for the electron spin are still there in the combined system's wave function.
Okay. That's a really different way of seeing measurement. It's not about collapsing possibilities. It's about creating connections.
Right. It's just another interaction that leads to entanglement and correlations.
So if there's no collapse, how do we, as observers, end up experiencing definite outcomes? This is where the observer themselves become part of the quantum world.
Right, exactly. In relative state, observers aren't some magical outside force. They're physical systems, just like anything else, following the same quantum rules.
But what about our conscious experience? How does that fit in if all the possibilities are still there in the wave function?
That's where Everett brought in this idea of memory. He said the observer's memory, which is a physical record of their experiences, plays a crucial role. Different memory states correspond to different experiences.
So when I measure something and see a result, that result is stored in my memory. Just a physical state of my brain or maybe some recording device.
Exactly. And Everett defined what makes a good observation. It's an interaction that, if the system is already in a definite state, leaves that state alone and changes the observer's state to reflect what they observed, like storing that observation in their memory.
So if I measure an electron that's definitely spin up, a good measurement keeps it spin up and also creates a memory in me of seeing spin up. Makes sense.
Right. But now, what if we measure a system that's in a superposition, like our electron being both spin up and spin down at the same time? Well, because of the superposition principle, the final state of the whole system, the electron plus the observer, becomes a superposition too. Each part of the superposition has a different outcome and a different observer memory that goes with that outcome. This is where the branching happens.
Hold on. Let me try to get this straight. So if the electron is in a superposition of spin up and spin down, after I measure it, the whole system becomes a superposition of electrons spin up. In there, I remember seeing spin up. Plus, electrons spin down. I remember seeing spin down. Like, both realities exist together.
Precisely. The universe has branched. In one branch, the electron is spin up, and there's a you who saw spin up. In the other, it's spin down, and there's a you who saw spin down. And both branches exist at the same time as parts of the universe's wave function.
Whoa, okay. So each branch has a definite outcome and a matching observer memory. It's like each version of me is only aware of their own branch.
Exactly. And that's why, as Everett pointed out, an observer in one branch never knows about the branching. Their whole reality is just what happens in their branch.
So we have this constant branching, and in each branch, it seems like a definite outcome happened. But what about probabilities? Why do some outcomes seem more likely than others?
That's a really important question. In relative state, probabilities aren't fundamental. They come from the structure of the wave function itself and from a concept called measure.
Measure. What does that mean in this crazy branching universe situation?
Think of measure as a size or weight we can give to each branch in the superposition. Everett said there's a way to define this measure based on a simple idea. The total measure of a bunch of branches should be the sum of the measures of the individual branches. It's called additivity.
That seems pretty reasonable.
It is. And when you apply this idea to the branches, it leads to a cool result. The measure of each branch is proportional to the square of the amplitude of that branch in the wave function. And remember, in the standard view, the probability of an outcome is also the square of the amplitude.
So the size of a branch in the multiverse basically matches the probability of observing that outcome in the standard interpretation.
Exactly. Now imagine an observer doing lots of measurements on identical systems. Each branch represents a sequence of outcomes stored in the observer's memory. The overall measure of a branch is the product of the squared amplitudes for each outcome in that sequence.
So if an outcome has a low probability, a small squared amplitude, then all the branches where that outcome happens a lot will have a small overall measure.
Exactly. And branches with highly probable outcomes will have a larger measure. Everett showed that for most observers in those high measure branches, the frequencies of outcomes match perfectly with the probabilities from standard quantum mechanics.
So the randomness we see isn't really fundamental. It's because we're stuck in one branch. And the chance of being in a particular branch depends on its measure.
You got it. From our limited view, it looks like the system randomly jumps into an eigenstate when we measure it. The probabilities we calculate are just a reflection of the measure of the branches.
It's like classical statistical mechanics, where we use probabilities for lots of particles, even though each particle follows deterministic laws. Here, the fundamental law is the deterministic wave function, but probabilities come from the branching of our experience.
Great analogy. Just like we use Lebesgue measure in statistical mechanics because it makes sense with the deterministic motion of particles, we use squared amplitude measure here because it fits with the additivity of measures and it reproduces the predictions of standard quantum mechanics.
This is amazing. And what happens when multiple observers look at the same system? Do they agree on what they see?
Absolutely. If multiple observers measure the same thing, their memories become correlated within each branch, so they all record the same outcome in that branch. It also resolves those quantum paradoxes, like the EPR paradox with entangled particles. The correlations are already there in the wave function, and each observer just sees what's consistent with their branch.
Wow. So to summarize, Everett's relative state gets rid of wave function collapse by saying all outcomes happen in different constantly branching universes. We only see one outcome because we're stuck in one branch, and the probability of being in a branch depends on its measure. And all of this comes from the deterministic evolution of the universal wave function.
That's a brilliant summary. It's a simple causal theory relying on just the Schrödinger equation. Yet, it still gives us all the probabilistic predictions that we know and love from quantum mechanics.
And it solves those conceptual problems with observers and probabilities. It's like a more elegant, complete picture of the quantum world.
Exactly. And it might even help us with even bigger challenges like unifying gravity and quantum mechanics. Because in those situations, the idea of a separate observer doesn't really work anymore.
This has been an incredible deep dive. It makes you rethink what reality even means. All those possibilities actually happening somewhere in the multiverse. It's almost too much to grasp.
It really challenges our intuitions. Think about it. What does it mean for free will if every choice you could have made actually plays out somewhere? Or destiny? Does each branch have its own future, totally separate from the others? These are the questions that Everett's theory makes us confront, pushing the limits of what we thought we knew about reality.
Absolutely mind-blowing. This has been a fascinating journey through Everett's relative state formulation. Thank you so much for explaining it all so clearly. I'm sure our listeners have a lot to think about.
My pleasure. It's a truly fascinating and thought-provoking area of physics. There's still so much to explore and understand.
And to everyone listening, thanks for joining us on this wild ride. Keep those brains buzzing, and we'll see you next time for another deep dive into the mysteries of the universe.